Good morning, student. This is work, energy, and power. The third part of the concept we will be discussing in this class, student. Today, another very important concept related to conservative and non-conservative forces. But before that, we will try to solve some example of those forces, student. First, let's see work done by mg force, student. Suppose, student, this is the inclined plane. Here one block is kept. This height is h, mass is m. This block drops to here. How much is the work done? So you have already seen, student, work done by mg force. Force into displacement in the direction of force. The force is acting mg. Displacement in the direction is h, student. So work done is mgh. Now suppose, student, this block is first brought along this way. And then along this way. First path, second path. So work done in first path, student, by mg force. See, the force is always acting downside and the displacement was perpendicular, so work done in path 1 is 0. And in the work done by path 2, if you see, this is the direction of force and the displacement is h. Work done in second path is mgh. So total work done mgh. Either you bring this object from here to here or you bring it from here to here. Work done is same, student. Now, student, let's look at another part of it. Suppose the ball is thrown upward, student, and then it comes back. So work done in the upward direction by mg force. This is displacement is x, student, final height. Now, student, force is acting downside, displacement is upward. So work done will be negative, student, upward. Now when the ball is falling down, student, the work done will be mg. So total work done is G. So, student, what you noted is, in the first part, the work done was independent of the path, same work done. And in this case, work done was 0. Means this is known as closed path, student. So work done in a closed path is 0. This is the nature of the mg force, student. 2 points we have noted, student. First is work done is independent of path, and second is work done is in a closed path is 0, student. Now, student, let's look into the spring force. Work done by spring force. This is the spring, student. This is the natural position. From here, suppose the spring is compressed, student. To this position. Now, how much is the work done, student? This is, student, variable force. So work done for variable force, student, we have already seen F dot dx, student. This Fx minus Kx, student. We already know the nature of the spring force, student. Force is opposite to the displacement. When I am compress it, the force is acting along this way. And here is the limit, student, initial position to final position. So if you integrate this, student, you will get x square by 2 this student comes out to be, so finally student, work done by spring force comes out to be K x1 square minus x2 square upon 2. Here student, what we have to remember, one point is this x1, this x1 is the initial elongation or compressive position of the spring, and x2 is the final elongation or compressive position of the spring. This you have to remember, student. Now let's solve some questions, student. I am writing here work done formula. What we got is, student, suppose student, the spring is compressed first to 2 meter along this side. Okay. Now from here to here I have to find out work done. So in this case work done will be K by 2, student, x1 initial position is 0 here, student, minus 2. So this is minus 2k. Minus 2k, student. Now suppose, student, this is the first case. Second case, this is the initial position. This is original length, student. Say this is 3 meters. Okay. From here the spring is again compressed. This is 5 meters, student. So how much is the work done from here to here? How to find out, see, student? Work done, the formula x K by 2. x1 initial elongated position or compressed position, it is 3. So 9 minus final elongated position or the compressed position from the initial. So this is 5, student, is 25. So 9 minus 25, student, 16. So it is minus 8. And see, student, work done is negative. Because we are compressing this side, the force is acting this way, student. Now, student, suppose, let's look another question. This is elongated by 2 meters this side, student, and again it is brought back from here again up to here. It comes back. So this journey you have to do, find the work done, student. So in this case the work done will be, student, K by 2 x1 square minus x2 square. Initial position 0, final position also 0. So work done is 0. So this is, student, closed path. So work done in closed path is 0 by spring force also. So this is the similarity which the mg force has with spring force, student. Remember this similarity, student. Now let's solve, student, one more question. Suppose, student, this is 2 meter, this is 2 meter. This is the original length of the spring. From here 2 meter compressed, and from here again the 2 meter from this side. So how much is the work done in this case? K by 2 student. Initial position 2 square 4. Final position student again 4. So in this case student, total work done from here to here is 0. Now let's look another question student. Suppose this is the case. There is a spring having spring constant 100. From here the spring is elongated by 2 meters. How much is the work done student? So here student, you have to understand one thing. The formula which we know, the work done by spring force, work done by spring force is this. But here remember student, initial position, this is not the initial position student, this is not 0, this is the mistake what student made. Remember this is not 0 in this case, because this spring has the original some different length. When this block was attached, from here it elongated up to here, say it is x. This x, you can know it student by the FBD diagram. If you draw it, this is mg, this is at rest, this is kx. So kx is equal to mg student, k is 100, x is equal to m is 5g. So x is student 50 upon 100, so it is half. So this half is the initial position of the spring student, initial. One more thing student, this was the initial position, half plus 2 means from here the spring was stressed up to here by the help of this. So this final position will be student 2.5. This is half 2.5. So now the work done by the spring will be half square means 1 by 4 minus 2.5 square. 2.5 square means 625, 6.25. This is you have to remember student in this type of question. How I have found out x1 and x2. This I have stressed it by 2 meter. So from here I have to take the length. How much is the stretch? This you have to understand student. So this is work done by spring force. It has a similarity with the mg force. That work done is independent of the path. And work done depends on the initial and final position, and work done in a closed path is 0. Now let's see student work done by friction, kinetic friction force. Work done by kinetic friction force. Suppose student, this is the table. One ball brought from here to here. This is 2. And suppose this length is 2. Okay. First I am bringing this ball from here to here. So when I am bringing it student, the kinetic friction force will act in the opposite way. So the work done in this path 1, kinetic friction force is given by student mu mg. So it will be given by mu mg into 2 and it is negative. Displacement is along this, friction is along this. Now if I bring this ball first from here on this path. So these are the two paths I follow. Now the work done will be student along this path, this minus mu mg into 2. Again student along this part total work done minus mu mg into 2. So total work done will be minus 4 mu mg. Now see student, when the ball was brought from here to here, work done was different. When the ball was brought from different path, work is different. So this means here the work done is dependent on the path. So friction force, it is work done is dependent on the path, student. One more thing student, the work done is negative. So but remember it, work done by friction force is not always negative. Okay. So this I will show you by the help of an example. This is the one block student. This is another block A, block B. This side force is applied. So this will apply force of friction along this side. And this will apply force on friction along this side. So now see student, work done by, now this body is displaced in the forward. So work done by this force is positive. So this means work done by kinetic friction is not always positive or not always negative. This you have to remember. Work done by this force is negative student. It is moving forward. But work done by this friction is not negative, it is positive. Force and displacement in the same direction. So work done by kinetic friction force is not always negative. Okay student, it may be both, positive also, negative, both. This you have to, generally it is heard that friction work done is negative, it is not always. That you have to remember student. So student, till now we have seen three kinds of, one is mg force, second was spring force, and then friction force student. So what we noted is, in the mg force and spring force, work done was independent of the path, work done dependent on the initial and final position, and work done in a closed path was 0. So this kind of force student is under a category known as conservative force. Conservative force. Conservative force means the work done by this force is independent of path. And second, work done by the force in a closed path is 0. And third, work done depends only on initial and final position. And this, the example we have already seen, mg force, that is the gravitational force. Then spring force. We have also some other electrostatic force also is there. It is a conservative student. Spring force, electrostatic force, spring force student. And just the opposite of it, conservative force. Example you have seen, kinetic friction. Many other viscous forces also there, which we will be studying in the later part. So conservative force, work done is dependent on path. Here dependent will come. Second, closed path is 0, not 0. And it does not depend, does not will come, just the opposite part will come, student. So these are the two categories of forces, student: conservative force, non-conservative force. The total mechanical energy is conserved, as you said. That energy is, student, remember it is for conservative forces. We will come into the detail and the later part of it. Though the total energy is always conserved as a whole, universal law of conservation of law. Now, student, we will discuss about the motion in a vertical circle. An object tied at the center, or somebody is holding it from here, it moves in a vertical circle, student. This is the ball of mass mg with the tension acting circle of radius r. Now at any time, suppose this is the position is here. This is angle theta, student. These are the forces which are acting. This angle is theta, mg cos theta, mg sin theta. Now, student, this ball would have gone this way, but this means something is binding it to move in a circle, and that is centripetal force, student. Centripetal force. So at this position, student, how much is the centripetal force? T minus mg cos theta mv square by. Now, student, let's see this position. Top. Here the forces which are acting is tension and weight. At the top, student, this equation becomes T plus mg is equal to mv square. Now, students, suppose I reduce the velocity. So this tension is an auto-adjusting force. It will adjust itself. But this is not an auto-adjust. This will not change. So suppose I go on reducing the velocity till the tension is adjusting it. And after that, tension becomes 0. So that is the minimum velocity which is possible, student, by the help of which the circle, vertical circle, can be completed. So for that minimum velocity, this t is 0, student. So I will write f v minimum square is equal to mg, student. So this velocity, minimum velocity at the top, will be given by under root rg. This is the minimum velocity possible, student. Now at the top, student, total energy. One is mechanical energy plus potential energy. With respect to this point, this is at a particular height, student. So this will have potential energy. So this radius is r. So this will gain potential energy by mg into height plus kinetic energy, student, half mv square. M and this velocity I am taking minimum velocity, student, v square. So the total energy at the top comes out to be, student, 5/2 mr. This is at the top. Now student, what is the velocity at the bottom here? So law of conservation of energy, student, mechanical energy is conserved. This total energy is converted into kinetic energy here. Half m v, I am writing bottom. So student, this velocity at the bottom comes out to be 5 r. So this means, student, this is the minimum velocity required at the bottom here, so that the circle can be completed. So this is what then the circle, student, that motorbike maintains this velocity, student, at the bottom, and that is why it does not fall down. As you know, when the bucket is also moved, student, water does not split up. Why the water does not split down? Because, student, the mg force is there. It is used up in centripetal force for the circular motion. So that is why that water is unable to fall down, student. Now see there is one more explanation of this, student. If I see the bucket here, okay, student, after some time the bucket comes this way, bucket comes this way. So if you, on the other way, if you see the drop, water drop, see, it is here, now it is here, now it is here. Ultimately, water drop is falling. You can see this way also, but it is not falling on the ground, student. So there are two ways of explaining this, of the why the water does not drop when the bucket is moved in the horizon. This is the condition which should be met. At the bottom, this is the minimum. This is the velocity which is required, student. Then only the vertical circle can be completed, student. So this is, student, the motion in a vertical circle. We can find out energy at any point. Suppose when the particle is here, you can find out the energy, student. This energy is converted into here. It will have potential as well as kinetic in this position. You can find the velocity also here. How much is the velocity? You can find the, see, if I want to find it here, student, how will you find it? See. This is r height, okay? R height, student. So here it has gained potential energy plus kinetic energy, half mv square. This I am naming it as C, student. Now here, how much was the total energy, student? It was having 5/2 mr. From here you can find out the velocity here. With this C, student, all are known quantities, this velocity can be found out, student. So you will see velocity is different at different points. So it is an accelerated motion, student. It is an accelerated motion. Now see one more thing before we about the spring, student. This is the spring. Say when it is this is the initial position, student. When it is compressed, student, it comes back here and then it overshoots due to inertia, and then it goes like this, student. So if you see, student, here student, it possesses potential energy. Kinetic energy is 0. At this point, when it overshoots, it has kinetic energy, student, maximum. potential energy is 0. Initial position it is. Now it comes back here, student. Again it has potential energy and kinetic energy as 0. So can you see, student, how the energy oscillates, student? And in between it possesses both kinetic and potential. So if I show it by graph, student, see. This is energy. This is distance. So this distance, say it is x. This is minus x, student, okay? So student, here at minus x, the energy is potential, means this. And again, student, when it is here, plus x. This is the energy it has, student, and here this is the energy, student. Potential energy is this, at the extreme. And student, if you see the formula of the spring, potential energy is, student, half kx square. Energy is having a square, so the shape will be parabola, student. So this is the potential energy curve, student. Potential energy. Now here at the mean position, kinetic energy is maximum, student. See this. And here kinetic energy is 0, here 0. So kinetic energy curve will be like this. Again, it's a parabola, student. This is kinetic energy. But total energy at any instant is constant. See, mechanical energy is conserved, student. Okay, student. Again, we will continue in the next class. Thank you, student.